Hello, folks. Hope you all had exciting time to create the final project. We are gathered here today to see the demo of a function as a service platform, specifically Arithmetic as a service platform. The team members would be myself, Rajesh, Tarun, and Mao. Let's take a closer look at the formal problem statement. At the user level, the problem statement would look as follows. When the user makes a request in the form of an arithmetic expression to the FAST API, it intends to exploit optimally the unbounded resources at the disposition and get served the reply at the quickest. Now, solving this user level problem reduces to the following distributed system level problem, where we build a fast platform, a serverless platform, would be responsible for dynamically starting and stopping the containers or VMs as requests arrive. The basic components of which would be a load balancer, a queuing system that can buffer requests, an autoscaler that decides when to add or remove nodes. That would be the formal definition. Let's take a quick look at the use case diagram, where the user has this certain functionalities and we take help from third-party services as follows. Moving ahead to the component diagram. So here we can see a component diagram. Our fast system is modularized as 3 broad independently existing services, namely HTTP service, responsible for the functionality of calculating expression and getting expression, parser and scheduler service, responsible for the functionalities of triggering the parser and making the gRPC calls, the cluster service, which is responsible for the functionalities related to creating pod, getting pod, deleting pod, creating service, getting service, and deleting service. Right. So given that we have taken a closer look at the component diagram, let's take a minute to explain step by step one round of the honest execution. We note that when we talk about an honest execution, we assume that the particular scenario does not have any fault or any autoscaling event happening, namely a message burst. For any further details, I would like to point the folks to the write-up. So the user makes a function request in the form of a parameterized arithmetic expression. The HTTP service takes the expression. The calculate expression function inside the HTTP service is responsible for allocating the unique request ID. The calculate expression function then enqueues the request in the inbound request queue. The cluster service is independently responsible for doing the following setup. It pulls the images from the Docker repository, makes the pods with these images at static port. Metadata information about the set worker and its replica gets stored at the etcd. The parser and the scheduler handler does the following. The parser and the scheduler handler dequeues a request from the inbound request queue, breaks the request expression into dependent and independent sub-expression, enqueues the independent and dependent sub-expressions into the respective layers of the 4-layered message queue. For each of the independent sub-expression, the scheduler makes immediate gRPC calls to the port of the respective K8 load balancer port ID. For each of the dependent sub-expression, the scheduler sleeps and wakes up periodically before making gRPC calls for each dependent sub-expression at their respective load balancer port ID. Now, upon getting a gRPC call, the load balancer for operation LBF does the following. Allocates function F to an available worker F. Worker F computes the functionality F. Worker F sends F to its leader replica, say RLF. RLF computes the function. RLF also does the following. RLF broadcasts pre-prepared messages to all the follower replicas RF. RLF broadcasts prepare messages with F to all of the follower replicas RF. Each of the RF computes F and returns a quorum certificate message, which we call a commit message, with the result of F to the RLF. Now, RLF, upon receiving 3 such commit messages with the same result of F computation, considering a scenario of 4 replicas, sends back the result of F to the worker F. Now, the worker F sends the result of F to LBF, which is in turn responsible for returning the result to the scheduler. The scheduler puts the result of the expression into the outbound reply queue. The HTTP service takes the result of the full expression. The get expression function inside the HTTP service is responsible for dequeuing the result of a certain request ID from the outbound reply queue. Calculate the final value and returns the dequeued result to the end user. So that's an honest execution. Let's go ahead and address the challenges of distributed systems that we have addressed. So we do manage to address majority of the DS challenges as described in class by our beloved professor. Three major challenges that we directly mitigate, meaning for all of these three challenges, we present customized solution algorithms and consequent empirical instantiation to the algorithm. Let's go ahead one by one. Failure handling is handled by our simple PBFT, where instead of 4 traditional sequence of message exchange, we design a simplified version of the algorithm as a sequence of 3 message exchange. Autoscaling is handled by static simple algorithm, an overview of which would be that if the length of the message queue for a particular arithmetic operation exceeds 4, then invoke worker pod for that particular functionality. Concurrency is mitigated by parallel parsing of dependent subexpression of the whole arithmetic expression. We point out that the green colored challenges are necessarily implied by the blue ones. It is needless to say that the gray colored challenge do not hold water in our particular backdrop. So we will be showcasing demo of 4 out of the 5 of these independent events, and we will be analyzing the empirical analysis and how it compares to the asymptotic analysis. So event 1 would be the distributed correctness. Event 2 would be a dependent expression. Event 3 would be fault at follower replica. Event 4 would be fault at worker replica. We do know that we will not be showing demo for this particular instantiation. Event 5 would be message burst. And for future work, it would be exciting to analyze solutions to fault at control plane. And it would be interesting also to analyze the empirical complexity analysis of autoscaling via Kalman filtering versus static autoscaling algorithm. Let's move on and go ahead to the demo.
So yeah, hi everyone. So our system is a distributed computation system, and we have developed with 3 services and 4 RPC images and queuing systems with SQS. And the SQS, we are having the inbound queue, outbound queue, and the scaling queues. And we are having the 3 services are the HTTP service, cluster service, and the parser service. The HTTP service gets the request, and the HTTP service is a user-facing service. Exposes 2 routes. One is to do the calculate expression, and the other one is for the get expression result. This calculate expression route will be triggering the HTTP service to do the calculation. The HTTP service logs the request inside the database request log, and also along with the logging, it also puts into the inbound queue. And to showcase the auto scaling and the number of pods and the thing, we are having a Kubernetes dashboard which showcases the deployment of pods and how many pods are running for each and every functionality. So we are going to trigger the end user request via the postman, and the parser service this does the calculation and the parsing of the expression. So to showcase the simple execution, we are going to start the initial system using by starting the cluster service, which creates the initial set of pods that are required for the system to be up. So we are creating the initial set of pods. There are 4 initial functionalities. For each and every functionality, we are creating 4 pods. So these 4 pods are coming up right now. So once these are up, we are going to trigger the simple calculation request. So now I'm triggering a simple calculation request as an end user. The HTTP server responded, and it has given the request ID. So the next step of the HTTP service is to put that into the inbound queue. And the inbound queue will trigger the parser service. The parser will be doing the calculation, and the parser will be putting the result into the message queue. You can see the message into the queue. This message queue, the parser that is placing is the outbound queue. That outbound queue in turn triggers the update result of the expression route that has been served by the HTTP service. That HTTP service this update result of the expression will be updating the result of that particular request inside the database logs. You can see here in the database logs, the request, this is our request ID 16, B16. You can see here, this is our request ID B16. So now this request ID, the user uses to get the expression result. So you can see here, I'm placing this, get expression. So now this, yeah, this is the route, get expression result. So now the user got the response. So this request ID has a request body as this one, and this is the one that we gave 1551, simple. And the response we got is the 2550, and the time taken is 43, and it's just taken only 1 second. That's great. So now the cycle is like this, like in this between 1 second, if the user triggers this get expression result, we are going to say that, hey, your result is not yet ready, come back after some time, because the HTTP service just checks the database logs, and then if there is no response, it means the response is yet to calculate by the parser and put it to the outbound queue. So now let us see how the complete system is working. So once the HTTP service puts into the inbound queue, the inbound queue will be triggering the parser service. This parser service is exposing a route called trigger parsing. This route is going to do the parsing of the expression and using the shunting yard algorithm, and then segregating the dependent and the independent expressions. Here where the concurrency comes, the dependent and the independent expressions, the dependent functions will be waiting and the independent expressions will be doing the calculation first. So now if you see here, the calculation, the parallel calculation we are doing with the Go routines. So this Go routine is going to call the RPCs, the RPC subtract, addition, multiplication, division. You can see here the subtract will be the subtract call. This subtract call will be calling the ports IP address, and the subtract method, which is our remote procedure, which does the calculation and responds the result, and this response we are sending back to the parser. So now the parser aggregates all these results and computes the final result. The scheduler computes the final result and puts it back into the outbound queue. So this outbound queue will trigger the HTTP service for the update result of the expression. This update result of the expression will basically update the result in the database. So now the user request is served successfully. So we are handling the concurrency using the dependent and independent expression, segregating and doing the calculation of the independent first and then later the dependent. And you can see now to showcase the auto scaling, I have prepared a curl request list, and let's run the curl request list. So I'm doing the request first right now. So the request is happening. Success. The request first has happened. So now, if you see here in the database logs, so the request was happened, and some of the results are okay. I'm sorting it by date. Some of the requests are served, and some of the requests are yet to serve. And you can see the pods are increasing. This is because since there's a request first happened, we have put the threshold as low, and which auto scale the required number of pods for the functionalities, and it auto scale the respective functional pods. So this you can see the request log here. So it has done the calculated expression and the update result of the expression back into the HTTP service, and there is an update deployment. So the update deployment is also happening, which is basically to update the number of pods required for each and every functionalities. So this showcases the auto scaling of our system. So based on when there is a request bus, it will auto scale the number of pods that are required for the computation, and then it handles each and every request. And we are gonna So this database logging and using the queue system and using this, we are not losing any of the end user requests. We are serving each and every request from the user. So we have deployed all this inside the EC tools like the cluster, the queue master and the queue worker. This queue master consists of the control plane and the queue worker consists of the all the pods. And these two are linked to each other, and there's HTTP service and the parser service. And the cluster service is present inside the master, which basically acts as an interface to communicate with the cluster to create the pods, update the pods, and then services. So to give you a gist of the cluster service, here is the cluster service. So what does the cluster do? It exposes some routes, and also it does the initial pod creation when the cluster service has been started. Initial pod creation for each and every pod, for each and every functionalities. So you can see here, these are the list of the functionalities that we are supporting. And these type of pods will be created at the initial. And we're doing by the node port, and we're specifying the port that is being exposed outside the cluster. This is how the cluster service is working. So now, to showcase the SQS, here are the SQS consisting of the inbound queue and outbound queue and the auto scaling queues. We are using the auto scaling queues when there is a add expression scheme. So we are pushing out into the auto scaling queues, and in a similar fashion, we are doing into the multiply, division, and subtraction. So the scheduler checks the auto scaling queues before assigning it to the particular pods. It basically, if the number of requests are more, the auto scaling queue messages will be more for the respective functionalities. So which the scheduler will basically trigger the update deployment route that has been exposed by the cluster service to increase the number of pods for that functionalities, and then assigns the request to the particular functional pods. This is how the auto scaling queues are helping out in the auto scaling procedure. So that's it. This is our distributed computation system, which can handle the concurrency and auto scaling. And then we are exposing the service with the REST endpoint. And the code base is available here. All the gRPC images and 4 gRPC images for each and every functionality and the services, the services, HTTP cluster and the password. And we have deployed the images inside the Docker Hub because this cluster will be talking to the Docker Hub to get the images. Yeah, that's it. Thank you, everyone. So, hi, everyone. This is a continuation of the previous video. Our project is a distributed computation system. In the previous video, we have shown the auto scaling and the concurrency. And in this video, we're going to show how our system handles the fault tolerance using the PBF. So now, we are having, as previously, we are having 3 services, cluster and the HTTP and the parser service, and respective functional pod images for the worker and the replica, and which we are going to deploy inside the cluster. And we are having a dashboard to showcase the number of pods and the deployments present inside the cluster. And we are having queues, inbound and outbound queues for the request handling to deliver the request to the parser, and also to deliver the response back to the HTTP service, which updates the response to the database. So at the initial, the user accepts the request via the HTTP service. Basically, we are exposing this endpoint to the user as an end user. He will be triggering the his computation expression via the HTTP, that expression, that route. And to showcase how the PBFT and the consensus process runs, I have created these 6 terminals. One is for worker, and the remaining one is for primary, and the remaining are for the follower replicas. So now let's start our system by creating initial set of pods that are required. Like we require etcd server in this system. So we are deploying the etcd server, and also we're creating a service for the etcd server. And we are starting our clusters service, which creates the initial set of pods that are required for our system. So in this case, the add worker and the primary replica and the follower replica. So you can see here in the dashboard, the pods are getting created. The etcd server is created, and the add replica and worker and primary and all this are created. Once these are done, our system is ready to accept the request and handles the fault orders. So now, I'm going to show you a simple request. Before that, I'll show you here the logs of each and every pods. So now we are having three replicas. One replica 0 is our primary. So let's see the replica 0 logs. So you can see the replica 0 is up and running, and is the server is and started the RPG server. And in a similar fashion, I'm going to show you the replica 1 logs and the replica 2 logs. Replica 3 logs. And the worker logs, where the request is being accepted and passed to the primary replica. So you can see all the pods are deployed and successfully running, and they are accepting the request. So now let's do a simple request. So I'm doing a simple request here. The user, as an end user, he just puts his expression here and triggers our system. And HTTP service successfully responded with the request ID, and it logged into the databases. Let's see here. Yeah, and it is logged into the database, and it successfully responded with the result as well. Because since the result is a simple, since the request is a simple request, the response, it got responded very quickly. And you can see the created date and updated date. So you can see the request came at 24 seconds, and the response at 24.5 seconds. So it has taken 1 second. So now let's see the logs of the services. Like you can see here, the HTTP service accepted the request, the calculation, and it has placed inside the database as well as inside the inbound queue, and it triggered the pass expression route by the inbound queue to do the passing, as well as triggering the worker to do the calculation and primary replica and respective follower replicas. So if you see here, and after the computation is successfully done by the parser, it puts into the outbound queue, and it updated the result using this. The outbound queue calls this route of the HTTP service, which updates the response back into the database, and user can access the result using the request ID. So now, to showcase how the consensus process has been taken place, these logs are helpful. So now I'm gonna refetch the logs of the worker. So if you see here, the worker accepted the result, and it has triggered the primary replica, connected to the primary replica, and it has sent the computation request to the primary replica with the operand 1 and operand 2 as 20 and 116. And this is our R0, replica 0 is our primary replica, which accepted the request and also started the consensus process and passed the request to all the other replicas. You can see the prepare, and the commit sequence messages here. And I'm also refetching the log of the replica 1, replica 2, and the replica 3, and the replica 4. So you can see every replica after the series of messages like prepare, pre-prepare, and the commit. So they have computed the result, and they are sent back to the primary replica. And once the primary replica got the result and completes the consensus process, it sends the result back to the worker, and the worker gets the result. You can see here the value, and the worker sends back the result to the parser, and the parser takes up from there and aggregates if there is a big expression and puts it back to the outbound queue, and the outbound queue triggers this update result of the expression, and this update result will be updating the result in the database. So now, here, let's complete this data expression for this particular. So I'm taking the request ID. You can see a user is able to get the response. So now, to showcase the fault handling, I'm going to delete a pod forcefully from our dashboard. So here are the pods, right? I'm deleting the pods, delete, and I'm going to retrigger the request with a different value. I'm retriggering the request. So yeah. So let's see logs here. So 20 plus 1600. So the request came and it responded back in 3 seconds, and we can see here. So even if there is a fault in one of the follower replica, we are successfully able to respond back to the user. So we are able to handle one fault, and if this replica fault which happened forcefully, so we are placing an event into the event bus, and we are handling it while assigning the request. The worker replica handles the fault at the follower replica, and recreates the replica 4 that we forcefully deleted. So let's see the logs again of the worker replica and the replica 0 primary, replica 1, replica 2, 3, and 4. So you can see here, we have forcefully deleted the follower replica, R4. So that's the reason the R4 doesn't have the logs. Because when it recreated, the name of the R4 pod will be different. So yeah, that's the reason. So even if there is a fault, we are successfully responding back. You can see 1620 is computed by all the other 3 replicas, and they send back to the primary replica and to the worker replica, and the worker replica send back to the parser and to the outbound queue and to the HTTP service. So yeah, this showcases the fault tolerance of our system. And yeah, we also developed a simple repository to fetch the etcd key value store, which fetches the etc key value store and the IP addresses and the ports where they're serving. So this is useful for the communication, and because these pods are acting as a set, because you can see 1, 2, 3, 4 plus 2. All the 6 pods are handling only one request, because one request, it is going to the worker and then to the primary replica, and then does the consensus. So all these pods are acting as a set. So to make them as a set, we are using the etcd server to store the key value pairs, and every replica will be knowing his his neighbors. Like, I mean, either it's a replica primary or it's a worker. Like, we are fetching it. The etcd store is a common storage for the key value pairs. So yeah, that's it. This showcases the fault tolerance in our system. Yeah, thank you.